Okay, let's do some applications. The very first problem, first of all, a bunch of formulas at the very top, be it simple interest, compound interest, then you have compounding continuously or continuous compounding, then effective rate of interest. So I'm just gonna take you through a few of these so that hopefully you can see a couple examples and see how it works again. All right, so first one, $100 invested at 4% compounded quarterly after a period of 2 years. And all those variables are listed in your formula sheet. But like I said, it's good to see it done again. So sticking kind of with the variables we're given, so it says A, which is just our future value. P's are principals, so we're given $100. It says compound interest, talking about compounded quarterly, which means it's done 4 times in that 1 year. So when we go right here, we're gonna say 1 plus our rate. Well, it tells us 4%, but we're gonna write that as a decimal, and 4% is 0.04 when you move your decimal place 2 places to the left. Compounded quarterly, like we said earlier, is 4 times, so that n is the number of times it's compounded in 1 year. So over 4 raised to the nt. So once again, there's our 4 again, and t is being time. We're doing this for 2 years. And we'll punch all that in our calculator, and you should come out to $108.29. And what I've done is we've put a copy of this on Canvas, the actual work, along with a image of the calculator, so you can see it there. But this is just me kind of going through it in words as well. But the $108.29 represent the present value after, or future value rather, after 2 years of it compounding 4 times per year at a 4% interest rate, $100. All right, example 2 is $400 invested at 7% compounded continuously after a period of 3 years. Continuous compounding is more of a theoretical, I guess you could say, but it's not really theoretical. It's a maximum value that an account can gain interest as far as compound interest. And so a lot of finance people, it's an important concept for finance people to understand. That's that maximum value attained. I can go into this deeper outside these notes, and I might make a separate video for it, or I can just do it in tutorials if you're really curious as to how that formula is even developed. But go ahead and using that formula. It's our principal now, it's 400. And then it's E to the RT, where R is our rate, which is 7%, so 0.07 times, let's see, what is it, 3 years. Okay, and when we put all that in, it's going to end up being $493.47. Okay, our next section is talking about what would our principal need to be now in order for us to get the indicated amount after the given time period. So how much money would we need to have now to put in our investment on example 3 in order to have $1,000 after 2.5 years at 6% compounded daily? So compounded daily means it's going to be compounded 365 times per year. So we know that we're looking for $1,000 after this time period is done. We want to say how much money would we need to put in that account right now, that interest-bearing account. So then we just go and fill the rest of our formula in. 1 plus, it's 6% interest, so 0.06. And then it's compounded daily, so 365 times per year. And we're going to raise that to the power of 365 times the number of years, which is 2.5, so 2.5. Okay, so we would take all this, you can punch it in your calculator, 1,000 divided by that piece, it's going to tell us that we would need to invest $860.72. All right, the next one, we're looking for $80. We don't know our principal. We do know that it's compounded continuously. So this is that PE to the RT formula again. Our rate is 9%, so 0.09. And it's compounded continuously for 3.25 years. So 3.25, 3.25. That would tell us that our principal amount, once again, e to this power, divide 80 by that amount. We get $59.71 would be the amount we would need to invest currently. Okay, example 5 is asking for the effective rate of interest. So we're saying that our effective rate of interest right here using our formulas are the 1 plus our rate, which is 6%, so 0.06. It's compounded monthly, so over 12. Raised to the power of n, which again is 12. It's the number of times it's compounded per year. And we're going to subtract 1 off of that. Now tell us our effective interest rate, or rate of interest. Same thing. So R is 6.17%. All right, example 6. It's the exact same thing, except it's compounded continuously. So we're going to use a slightly different formula. When it's continuous, it maxes out with e. So it's going to be e to the power of our rate, which is 0.05. Again, we're going to subtract off that 1. So that would be 5.13%. And so just to make sure you understand what's going on here, effective interest rate is basically just the actual value we're getting from, say this was something we put like an investment in. So yeah, it says a nominal interest rate of 6%, but this is the effect it would have. This is what compounding would have this effect. It would be a 6.17% interest rate. So basically, effective interest rate is just taking compounding into account. And obviously, the more times it's compounded, the better our rate's going to be, our effective interest rate's going to be. All right, let's look at example 7. What rate of interest compounded annually is required to double an investment in 6 years? So I'm going to start this way. We don't know what our principal amount is, and you can make up a number here if you wanted, but just to kind of give it in a general sense. So say we had some principal amount, and we know that we are doing compound interest. So we're going to say 1 plus, and we don't know the rate, so we'll leave it as R. Over a number of times it's compounded. It says it's compounded annually, so just 1 time per year. Raised to the power of, what is this, 1 times, and we're going to do this for 6 years. Now, we don't know the amount that we're going to be necessarily investing. Like I said before, you could have just make up a number here, that's fine. But we do know that we're looking to double the investment, so we know that this side is going to be whatever our principal is times 2. And then we just need to solve for R. So what I would do is I would go ahead and divide that P over. So basically we're just saying, when is this equal to 2? And you can already see there's some simple things you can do here. Well, that's, 2, R of 1's R, so it's just going to be 1 plus R raised to this 6th power. And then we can go ahead and just do the 6th root on both sides to get rid of our exponent of 6. So I'll go ahead and leave that. The 6th root of 2 is equal to 1 plus R. So in our calculators, we just need to figure out 6 root of 2 minus 1 to determine what R is in this particular example. Looks like we're going to get 12.25%. All right, last example in the finance section. If Tanisha has $100 to invest at 8% per annum, that's just talking about per year, compounded monthly, how long will it be before she has $150? So we're figuring out, when is it equal to 150? That's the amount we're looking for. All right, and then we invested $100 initially. And we know that we're going to be going 8%, so at 0.08. It's going to be compounded monthly. And we're trying to determine how long it will be before she has it, so we don't know t. So leave it as t. So I would go ahead and divide the 100 over. You can make it a decimal or a fraction, doesn't matter, same thing. So 1.5 is equal to 1 plus 0.08 over 12 to the 12t. Okay, so this one's not quite as easy as the last problem because our exponent is not a 1 or 6. I'm sorry. Our last one was just a 6. This has a variable in it. So we're going to kind of approach this a little bit differently. We don't have a common base, but we can apply logarithms. I'm going to say ln. You could say log. It doesn't matter. It's the same thing. So ln 1.5. We'll do the same thing over here to this side. ln of 1 plus 0.08 over 12 raised to the power of 12t. Well, using our properties of logarithms, we know that we can move the exponent to the front. So now it's 12t times ln of all that mess inside of there. And then we're solving for t. So we're going to divide. So we have ln of 1.5. And we're going to divide the 12 and the ln of 1 plus 0.08 over 12. Obviously, there's a lot of different ways you can type that in a calculator. But essentially, you arrive at the same solution, or hopefully we do. You're looking at approximately 5.09 years. All right, just do some more applications. A little bit from the finance now. So a colony of bacteria grows according to the law of uninhibited growth, according to this function given, where n is measured in grams, t is in days. So looking at this 0.05, you look in the formula on exponential growth as a k. It's a positive constant that represents our growth. It's our rate. All right, so going through this, we got part A. Determine the initial amount of bacteria. Well, that would be 100. It's the amount right there at the very beginning. So we have 100 bacteria. B is what's the growth rate of that bacteria. That's that rate we were talking about earlier. So the 0.045, which we'll write as a percentage, so 4.5%. All right, part C. What is the population after 5 days? So we're looking for n of 5, and we know that n of 5 would be 100 e to the 0.045 times 5. So that population would be 125. We'll just say 0.232, just to go back to 3 decimal places again. All right. D. How long will it take for the population to reach 140 grams? Okay, so we're saying 140 equal to 100 e to the 0.045 t. We'll try to determine when does that occur. So the first thing we can do is we can just take this 140 and divide it by 100. Once again, you can leave it as a decimal or a fraction. I mean, it's not too bad to write as a decimal, which is 1.4 is equal to e to the 0.045 t. Okay, now we're going to incorporate our logarithms. So ln of 1.4 is equal to ln of e to the 0.045 t, which we can write as 0.045 t ln of e. Well, ln of e is just 1. Double check, make sure everything's good here. That you can see everything. Yeah, good. So ln of e is 1. So that's out. We'll just divide that with 0.045. So ln of 1.4 divided by 0.045 is what we need to put in our calculators. And we get looking like about 7 point, I'll just say 477. And obviously it's talking about days. So I better put that because it's asking for how much time in days, or T is days. All right, let's see if I can squeeze E in here. So E is, what is the doubling time for that population? So the exact same thing we're talking about we did earlier as far as doubling it. And I'll just go ahead and stick with the formula. So the double of 100 is 200. E to the, I'm just going to say 0.045 T. So we're basically saying when is 0.045 T equal to 2. So once again, we're going to incorporate our logarithms. So ln of 2 is equal to ln of e to the 0.045 t. ln of 2, we can move that to the front, 0.045 t ln of e. Same thing, ln of e is going to become a 1, right? So that's out. So I'm just going to come over here. ln of 2 is equal to 0.045 t. So we're trying to figure out what's ln of 2 over 0.045. So we're looking at 15.403. And once again, that's our days. So the population will double after a little over 15 days. All right, example 2 has to do with Newton's law of cooling. All right, so part A, make sure everything's loading here correctly. So part A is talking about the temperature of an object is 80 degrees after 5 minutes. Will its temperature be 50 degrees Celsius? This is given that it's heated at 100 degrees Celsius and is allowed to cool in a room with air temperature of 30 degrees Celsius. All right, so we know that, just using the formula, it's equal to 80. And then that first T represents, our temperature and our surrounding medium, which is our room temperature in this case, so 30. All right, plus, so the U aught represents our initial temperature of the object that we're heating. Okay, so that's 100 degrees. And then we're going to subtract off that surrounding temperature once again, so the 30 degrees for the room temperature. Now K is a constant, and you can look at this in different textbooks or online, and formulas change a little bit, but really they're the same thing. If you notice, it says K is less than 0, which means that K is negative. But just to keep this a little bit cleaner, I'll go ahead and just use a K, but just understand that it is a negative constant. Okay, and we don't know what that constant is yet. We're going to have to solve for first, but we know that we're doing this for after 5 minutes, it reaches 80 degrees. So we have ourselves a problem here that we need to kind of go through and solve and determine what our constant K is in this problem. So, I'll do it this way first. With 80 is 30 plus, this is going to become a 70. E to the K times 5. I'll just go ahead and write off the side. We know that K is less than 0. Just to understand that. All right, so continue going. Subtract our 30 over. All right, we can divide by our 70. So now we would basically have 5/7 is equal to e to the 5k. Apply our logarithms, so ln of 5 over 7 is equal to ln of e to the 5k. Remember, we'll move that 5k to the front, and that ln of e will just become a 1. So we're left with ln of 5/7 is equal to just a 5k. And then we can divide our ln of 5/7 by 5. So ln of 5/7 over 5 is what our k value is going to be. And you can do several things from here. If you wanted to, you could go ahead and type that in a calculator. Okay, or we can just leave it as is right here. Trying to think of the best way to kind of show you guys this. You could make it obviously same thing as saying 1/5 ln of 5/7. If you want to move that 1/5 as an exponent on that 5/7, you're more than welcome to do that as well. But either way, you're going to get the same approach no matter what. And just understand that this would become, a negative value. So I'm going to write like this. If you want to know what it was as far as a decimal, it's negative 0.0672 ... So like I said, there's several different ways we can represent that. But the question is not what our constant K is. It is, when will its temperature be 50 degrees? So we have this K value that we already know. Okay, and just to say one more approach, just to make sure you understand it. Remember, it could also be written as ln of 5/7 to the 1/5, right? ln of 5/7 to the 1/5, or 0.2, or whatever you want to say. All right, so let me just draw this right here just to kind of separate our work out a little bit. Here's our formula now. Okay, we know that we have 30. That's our temperature that we've been dealing with. And we're going to say U of t here. So 30 plus 70, because remember we initially heated it at 100 and we took off that room temperature of 30. E, all right, and we're talking about our K value now. So I'm going to write it as ln of 5/7 to the 1/5. All right, so you have all of that. Let's put it all in parentheses to kind of keep it a little nicer. T, that's kind of our formula. And once again, if you wanted to write that as a decimal, you're more than welcome to. But that's just kind of everything written in fractions. Nothing's been rounded yet. Just kind of be more mathematical, I guess you could say. And so what it's asking for is, when will the temperature be 50 degrees? So all we need to do is look at our problem and figure out where that 50 goes. Well, we know that we're looking for 50 degrees, so that's going to go with the U of t. So we're going to substitute 50 in place. So 30 plus 70 e to the, this is a big mess right here, ln of 5/7 to the 1/5 t. Once again, I don't know if I already said this, but just to reiterate, if you want to put this nasty decimal in that position, you're more than welcome to. But basically, we're going to take this 30, subtract it over, which will make this a 20. I'll go ahead and show that. So 20 is 70 e to the, that mess again. All right, we would divide 20 by 70. So divide that 70 over. And then you can already see that become 2/7 is equal to all this mess. And you can probably see that we're going to have some natural logarithms applied now. Once you go and apply your natural logarithms, you have ln of 2/7 over here. We're going to apply ln of e to all this power. Well, remove all that stuff to the front. And remember, we would have ln of e out here, which we know is just a 1. All right, so from here, you could have taken the e and ln, for that matter. I'm just looking at that right now, and just marked them out as well, which would have been a little bit faster way. But just to kind of be consistent, I guess I went ahead with this approach. We can move that 1/5 t to the front. We have the ln of 5/7. So we could then take the ln of 5/7, divide it over, along with that 1/5, and divide it over. So we're looking for that t value. So ln of 2/7 divided by 1/5 ln of 5/7. All right. So we should get, type it all in here, approximately 18 point, trying to decide how I want to write that, 18.6, I'll just stick with what we've done, 18.616. Long problem. But, and let's make sure what the units again on that problem. They are minutes, so 18.616 minutes for part A. All right, before we go to part B, I had a little sloppiness right here. I apologize for that. This t value, remember it was in our exponent for our e all the way through, and then all of a sudden I decided to put it on the exponent of the ln. So on this step right here, when we're talking about ln and applying it, remember this right here would actually be down here. Apologize for that. Now, it came out to be the same. We went down to this step. But just want to make sure I did point that out, that this ln of 5/7 to the 1/5 times t, right? Put the parentheses around this, times t times ln of e, which would then be the same thing as 1/5 t ln of 5/7. So I apologize for that little step. And just to kind of make things a little nicer, I wrote all these. I went ahead and wrote it in terms of that crazy fraction. For this next problem, I'm going to go ahead and use this k in the decimal form. Just understanding, remember that it does go on. So that's the stored value in our calculator. If you want to type that in your calculators and get this really nasty decimal, you're more than welcome to, because that's what I'm going to use when I'm doing my calculations. But I'm going to just write this decimal because it'll look way better presentation-wise than what would just happen. And then hopefully I can avoid that mistake again. All right, so part B. Let's see here. Determine the elapsed time before the object is 35 degrees Celsius. So I'm going to rewrite that formula that we determined, because remember we figured out what that constant was. So remember it's 30 plus 70 e to the negative 0.0672 t. And so all we're doing now is it's basically the same thing we did in the other problem. It's just that we've already determined k. So it just says determine time after 35 degrees, for 35 degrees rather. So plug 35 in for u of t. So it's 30 plus 70 e to the negative 0.0672 t. We'll take that 30 and we'll subtract it. We get 5 is equal to the 70 e to that negative 0.0672 t again. Divide by 70, let's see, 5 and 70 is like 1/14, I believe. So 1/14 is equal to our e to the negative 0.0672 t. All right, so now we're going to apply our logarithm. So ln of 1/14 is equal to ln of e to the negative 0.0672 t. So once again, where the ln of e is going to become a 1 after we move that to the front, our exponent, and then we can divide ln of 1/14 by that negative 0.0672. Remember, that's in our calculators though. So I'm going to write it up here. So our t value is ln of 1/14 over negative 0.00672 ... that value that you have stored. And you should get, let's see, what did I get here? 39.217. I believe this is minutes again. All right, so there's those two examples. Remember, first one's 18.616 minutes. we had to determine first everything on this left side, the k value, that constant value. And then part B was just using that constant once again to determine how long it would take to get 35 degrees Celsius. Okay, our last example. Example 3 has to do with fruit flies placed in a half pint bottle of milk, and we're just kind of looking at the population. So typically, when you're talking about populations in nature, especially, they follow this logistical growth model. So if you had that formula that you were given here, it has, this given to you. It tells you that A, B, and C are all constants. B being our growth, whether it be increasing or decreasing. We can go into that a whole lot more next year, or maybe the year after that in calculus, BC and AB, I think a little bit. But what I want to get across to you right now is that if B was getting really, really, really big, like a really large number, then this would become 1 plus A over, remember that negative, and move E to the bottom. So become a fraction where our denominator is getting really large. So it'd be 1 plus a really large fraction, a really small fraction rather, because it's a fraction with a large denominator. So essentially we'd be saying C divided by 1 plus 0, or basically C divided by 1. So C is an important variable. It's our carrying capacity. All right, so as B gets really, really big, this is what's going to be the value that we're approaching for our population. So as it grows and grows and grows over time, it's eventually going to get to this value that it can't quite surpass. And that's what we call our carrying capacity. So looking at part A, state the carrying capacity and our growth rate. So, part A is very simple. You're just kind of looking at your formula and analyzing it based on the things we talked about. So the first thing I'm going to look at is our carrying capacity. And you can see that the carrying capacity is just simply 230. Okay, that's our carrying capacity. All right, and then it also talks about our growth rate. Now, our growth rate, it says negative 0.037. You can just disregard the negative. You want to think of it as absolute value, you can. But basically, our growth rate right here is, well, we're not going to write 0.37, but rather going to write 37%. Okay, and this is going to be our growth rate. So it's just like we've been following earlier. Move that decimal place over 2. So in this particular problem, 37% is our growth rate, and our carrying capacity is 230. If you have questions on that, obviously we can talk about in tutorials. It's just me kind of going through the formula. Carrying capacity C, B is our growth rate. Let's go ahead and indicate it up here. Or decay. I mean, it could be decay as well, but we're just going to stick with growth for right now. And then A is our constant, which we would find, which is given to 56.5. All right, so part B. Part B is asking for, let me reread that again. It's saying, what is our initial population? Well, that would be when T is equal to 0. So, if you put P of 0 is equal to, 1 plus 56.5 e to the, I'm just putting it all in here, 0.37 times 0, 230. Well, e to all this basically just becomes e to the 0, which is 1. So we'd be left with 230 over 1 plus 56.5 times 1. So in our calculators, we can just take it 230 divided by 57.5 if you need a calculator. I think that comes up to be a pretty nice number. Should be getting 4. Let's double check it. Yep, so 4 would be our initial population. All right, part C is what's the population after 5 days? So we're looking for the population of our fruit flies. But so earlier, remember we talked about what was the population, our initial population is a P of 0, which I could probably should 4 fruit flies. I guess we should probably talk about the actual units, but there's 4 fruit flies after initially. And what we're wanting now is, what is the population after 5 days? So we know after 0 days it's 4. So what is it after 5? So same thing, just 230 over 1 plus 56.5 e to the negative 0.37 times 5. We can put all that in our calculator, and I think you get like a decimal around 23.27. 27 flies. So essentially we're going to have 23 flies after 5 days. All right, so there's that one. All right, part D. Part D is saying, how long does it take for the population to reach 180? All right, so we're looking for 180 as our population. It's given to us. And we're just going to fill in everything we have in our formula. So 230, 1 plus 56.5. All right, so all that stuff labeled in. Make sure you can see everything here. All right, so now we're just going to go about solving it. I'd probably take all this stuff in the denominator and multiply it over. So it'd be like 180 times all that mess. Is equal to 230. Okay, and then I'm going to try to combine a little bit of steps here. We would take this 180 obviously and divide it over. So we'd have 230 over 180. So then we'd be left just with this portion in the parentheses now. Well, we're trying to solve for t. We can go ahead and take that 1 and subtract it. So minus 1, that'd be our 1 taken out. And then we'd be left with this portion right here equal to 230 over 180 minus 1. So we would go ahead and probably divide by our 56.5 just to get that stuff further simplified. So now we'd be left with e to the negative 0.37t is going to be all that divided by 56.5. All right, so if you take that 230 over 180, right, and divide by 56.5, it's what, 518, so we're 56.5. Just to kind of keep things a little bit organized here, that's going to come out to, obviously this is a continuous decimal here, 0.0049 dot dot dot. All right, so the last thing we need to do is get our t value. So that's where we're going to apply our logarithms. So once again, we would have ln of e to the negative 0.37t is equal to ln of 0.0049 dot dot dot. All right, move all that to the front. The ln of e would just become a 1. So we have negative 0.037t is equal to ln of 0.0049. So t is all of that divided by negative 0.03, or negative 0.37, sorry. Let me just write that right there. Negative 0.37. This is too sloppy. I apologize, guys. Let me come up here. ln 0.0049 over negative 0.37. That's what we're going to have to put into our calculators. And I think you get approximately, let's see here, 14.365. And our units on this problem, looking at days. So 14.365 days. There we go. Make sure you guys can see that. All right. All right, our final problem here. It says using a calculator to determine how long it will take for the population to reach 1/2 of the carrying capacity. So just to make sure we understand that, half of 230 is 115. So it's 115 is equal to our formula. So let me get back to that page where I can read it. 230, so our numerator 1 plus 56.5 e to the negative 0.37 t all over, or all under rather, 230. Now I went ahead and worked this problem out earlier, just to kind of save some time. You're going to get t is equal to 10.903 days. Okay, now how would we solve this particular problem? It's the exact same way we just did the other problem, right? We had, what was it again? It was 180. So this time it's 115. And you just go about, remember, multiply this over with the 230 to 115 over by dividing. It's the exact same process except with a different number. One thing I want to change in your notes, if it says when it says using a calculator, what I really says use a graphing utility. I don't need to graph it. So when you graph it, and I know I haven't been able to show graphs, so I'll just go ahead and just draw a rough sketch real quick. You're going to have a logistic model. It's going to be something like looking very exponential at first, and then it's going to flatten out and kind of go like that. And it has these, these horizontal asymptotes. So you can imagine that this area up here, right, this horizontal asymptote I'm talking about, and now it's 230. That was our carrying capacity. But what we just now found was our halfway point, right? What was the exact words it was using? How long will it take for the population to reach half of its carrying capacity? So 115, if you graph it, you can put your equation in the graph, the 230 over 1 plus 56.5 e to the negative 0.37 t for y1, and then y2 you can plug in 115. So what you would get is you would get a line, just a different color, you would get a line that's going right through our curve. And once again, I know you can solve this algebraically, but I'm just looking for one little concept that you talk about here, and a graph is going to do it for us. So you can see that's where those intersect, and this intersection spot right here, it's saying when does that happen? When we know the y value 115, the x value down here would be the 10.903 that we just now found. Now here's what's important about it. Then I'll leave it with this. So you can see that halfway point. If you think of it, this population's increasing at an increasing rate. It's really increasing pretty quickly right here. All right, it's increasing at an increasing rate. But once it hits this spot right here, where it's half of its carrying capacity, once it hits that 115 was a fruit fly population, I believe. Well, then it's still increasing. In fact, it's always increasing, right? But it's increasing now at a decreasing rate. So right here, below the red line it's increasing at an increasing rate. And then it hits this spot, and now it's increasing at a decreasing rate, right? It's not increasing as fast, very quickly, and now it's beginning to slow down. This point right here is actually called an inflection point. Okay, that spot right there is called an inflection point. And when you get to calculus, y'all will talk about that inflection point way more in detail. But that's just something it's important to know. And we're doing logistics. It's really easy because you're saying when does the inflection point happen? Well, you know exactly when, where rather, as far as the population is concerned. It's just always half the carrying capacity. But if it's just asking for the answer, you can look for the point of intersection. It's just this right here, or you can solve it algebraically. As always, if you have any questions, please let me know. You guys stay out of the trees.